Erosion. It's a process that many people take for granted. Actually, it's a process that breaks down granite and other types of soil. But what is erosion? Erosion is when particles become detached. On a small scale, it's really not that impressive, but on a large scale, it's as impressive as the Grand Canyon itself.
And that's why we came to the Grand Canyon. Perhaps the world's greatest example of erosion. There are some phenomenal features here that are due to erosion. And so we want to learn about erosion theory, but let's just talk about the Grand Canyon for a moment. It's an amazing place. It is 277 miles long. Now that's a lot of erosion happening. But from here, where I'm standing on Navajo Point, to the North Rim, it is 10 miles across right here. And this place is deep, a mile deep on average. People who have done the math have put together the numbers to figure out how much dirt is missing from the Grand Canyon, and it comes out to 1,000 cubic miles. Wow, that is a lot of erosion.
But the Grand Canyon doesn't come without controversy when it comes to erosion. The controversy centers around how the Grand Canyon was formed. And it really boils down to this: two schools of thought. A little water over a lot of time, or a lot of water over a little time.
I, as an erosion professional and someone who's studied this, I look at the principles of erosion and sedimentation when I look at the Grand Canyon. And there's a few things in my field of study that tell me it was a lot of water over a short period of time. The first one has to do with where we're standing. We're standing on the Kaibab Plateau. That is an elevation of around 7,400 feet. And across from us, looking straight across, is the North Rim. That's over 8,000 feet high. Now, below us, the Colorado River is flowing from east to west through the canyon. And that's where the rub comes in. Because you see, to the east of us, it's much lower, and same to the west. So how did the water get through? How did the water gap form? There had to be a significant erosional measure or event to have created that. And so that's the first evidence that I have, that it was rapid canyon formation with lots of water over little time. Now the second one, if you look behind us, you'll see here that there are side canyons and amphitheaters. When we look at these side canyons, we actually see that there are no historic water sources of any significance. No historic creeks or rivers. So how did those side canyons form? That's always been a question. How did these beautiful amphitheaters form? Well, in erosion theory, there's this process called sapping. And when we have saturated soils with water and we have high flows moving perpendicular to them, it will actually draw out a lot of the sediments, the water soaked sediments will be drawn out and basically cave in and form these small little side canyons, you might say. We see this happen on construction sites, in stream beds on a much smaller scale, obviously, but the same principle is occurring. High flow, saturated grounds, giving way and forming these side depressions coming into the main area of erosion. And so another evidence that I point to is you'll notice that we have very steep walls and steep slopes. But if you look at the base of them, there's very little evidence of rocks that have fallen and built up, very little talus buildup. There's some, but not much, not accounting for long periods of time. Again, pointing to perhaps this happened in a relatively recent history.
But for me, I think the best evidence for rapid canyon formation comes from the erosion theory concept called dynamic equilibrium. The concept states that the amount of sediment eroded is directly proportional to the amount of water. You can think of it as a balance. On one side is the sediment load, which includes the amount of sediment and the particle size. On the other side is the hydrologic load, which includes the amount of water and the energy of the water.
If we're going to move a lot of dirt, we need a lot of water, is what the dynamic equilibrium talks about. But in that, it also addresses two processes that happens. So when we have a lot of water, when there's a lot of water, we get a process happening called degradation. And degradation is where we get a cutting of the stream bed or the river or the bank or whatever erosional feature we're talking about. So we get a deepening of those channels. Now, aggradation is the opposite. When we get a heavier sediment load, that sediment's going to want to settle out somewhere. And so it starts to settle out, and we start seeing aggregate in the stream beds. And that causes the flow to spread out. Now, if we take the Grand Canyon and the Colorado River watershed, we see a classic demonstration of degradation and aggradation. Right here, where we're standing, we see degradation, a distinct cutting. Definitely have removed a lot of material, steep walls, very much degradation. But if we go further down the watershed, outside the canyon, as we move further to the west and southwest, we get into these drainage fields where we see a lot of sand and sediment being deposited. But the telltale sign is how wide those drainage areas are. They're very wide. That is where the aggradation happened. So that dynamic equilibrium, to me, is the best evidence of rapid canyon formation over short period of time with lots of water creating it. So as an erosion professional, I look at the Grand Canyon and go, wow, it's playing out these principles that we work with every day, and that's really cool and pretty neat.
Okay, so viewing the Grand Canyon as a result of catastrophic erosion is pretty uncommon and maybe a little controversial. But is it really such a wild assumption? The rills and gullies we see on poorly managed construction sites are just scaled down versions of the Grand Canyon and exhibit the same erosional features. Do erosion principles become irrelevant as the scale increases? Also, catastrophic erosion on this scale is not without precedent. There are other gigantic erosional features in the western United States that are widely accepted as caused by catastrophic flooding or breached dams.
Glacial Lake Missoula was obviously formed by glacial melt. An ice dam held it in place, and finally, at some point, it gave way. Now, it may have been 2, 3, or more events. There may have been even several events. But that is basically what formed the scablands of eastern Washington and some very impressive erosional features like the Palouse Canyon. Take also into consideration the Snake River Gorge. The Snake River Gorge, very deep, very much a demonstration of degradation. But the Snake River Gorge was formed by ancient Lake Bonneville when it breached the dam at Red River Pass. It breached there, and the water flowed to the west and formed the Snake River Gorge. We even see examples like this more in the current times, like Mount St. Helens. There are some very impressive canyons that were formed over very short periods of time. In some cases, days, weeks, months at the most. Form canyons that are even deeper than 100 feet, having characteristics very similar to these other erosional situations that we see all over the western United States. Well, that's some of the history of the Grand Canyon. But what can we take away from here when it comes to soil loss, erosion, sedimentation? What lessons can we learn from the Grand Canyon? Well, that's what the United States government was wondering in the 1930s. When another catastrophe happened, this time a man-made environmental disaster, it was called the Dust Bowl. And it was a situation where farmers had plowed up copious amounts of ground. There was a lot of exposed soil open to the environment. And then when windy conditions came up, it basically created an environmental disaster. And so the United States government, through the Department of Agriculture, really began to study it and look at it. Why is this erosion happening? And what can we do to control erosion, to control sedimentation? What kind of conservation methods can farmers use when it comes to managing their fields in order to avoid this type of erosional event? So the Department of Agriculture formed this equation based on observations and empirical data. It was called the USL, the Universal Soil Loss Equation. And basically, it took all the data that they had been gathering and put it into one formula where they could come out with a way to predict soil loss, and also to be able to quantify the benefits of good soil conservation methods. Now, over the years, that equation's been refined and revised, and today it's called the Revised Universal Soil Loss Equation, or the Russell. The Russell is based on more evidence and more studies that have been done. But to understand erosion, we really got to take a look at the 5 stages of erosion. A lot of people don't realize that erosion actually progresses through 5 distinct stages. And I brought a graphic here to kind of illustrate that for us. And the first stage is the raindrop falling out of the sky. It's when the raindrop hits the ground and basically breaks loose other particles. Each raindrop's like a little miniature bomb, actually. It's traveling at 5 to 20 miles per hour. And when it hits the ground, it actually creates a microscopic crater. And the fines are blown out and it leaves an indentation. Now, one raindrop doesn't result in a whole lot of erosion, but you multiply that over millions, if not billions of them, it adds up. That's a lot of erosion occurring just from the rain hitting exposed soil. Now that leads us to the second stage, which is sheet erosion. This is when those raindrops come together and they start forming a thin film traveling across the exposed soil. That actually can account for quite a bit of erosion. But the problem is a lot of people don't really note it. It doesn't have those telltale signs that the next stages have. They might see brown water leaving the site, but they don't see the markings of it. But if you look closely, especially over a series of storms, what you'll notice is that the aggregate will start to become more pronounced. You'll start to see gravel and pebbles and coarse grains of sand. Well, why is that? Well, it's because the fines have been washed away. And that can actually account for a lot of erosion. Now that leads us to the third stage. And that's as the sheet flow condenses, it starts going through paths of preferential flow. It starts to form these little tiny channels. In erosion theory, we call those rills. And those rills are actually 100 times more erosive than the sheet erosion. And they will travel from maybe the top of the slope or midway down the slope, and they'll start forming generally after 10 to 20 feet of sheet erosion. Now, when those rills start coming together, that brings us to our fourth stage of erosion, and that's gully erosion. Now, the working definition of a rill is something that can easily be stepped over. It is pretty small. But the gully, on the other hand, this is something that you can stand in. You're not going to easily step over it. Erosion has progressed, and now we're gouging out a lot of soil. Gully erosion is 100 times more erosive than rills are, and now we got considerable soil loss. And that takes us to the final and fifth stage of erosion, and that is called stream bank or sometimes channel erosion. And this is where the erosion is happening more maybe downstream, off the site. It's more a watershed issue. It is cutting away the banks. Earlier we were talking about degradation. That would be a form of stream bank erosion, where we get the deepening of the sides, the cutting away of the stream banks. And so that is typically happening probably as a result of the other forms of erosion that preceded it. So that's why we came to the Grand Canyon, is really to look at this great example of erosion, some of these phenomenal erosional features, and to take the Russell equation and to use what we're seeing here in the Grand Canyon to help us understand this equation. Now here it is for the first time. It's A equals R times K times LS times C and times P. Now in the next 4 video lessons, we're going to focus on these Russell equation variables. But for now, why don't we look at what we're solving for, and that's A. Now, A is soil loss, but we got to give it a unit of measurement, so we're going to give it tons. Now, tons per what? We're going to assign it tons per acre, or we're going to say average soil loss per acre expressed in tons, but over what course of time? Well, those who developed this said 1 year, a whole 1 year cycle of a rainy season. So A equals the annual average soil loss per acre in tons. Now for alliteration purposes, just so it rolls off my tongue, lots of times I'll say average annual acre tons. But you know that we're talking about soil loss on an annual basis expressed in tons per acre. And so we're going to now take a look at this equation and what we can learn from the Grand Canyon. So why don't you grab your pack, maybe a water bottle, and we're going to head on over to one of my favorite locations in the whole Grand Canyon, and that's Hermit's Rest. And we're going to learn about the R value, but also about erosivity, climate, and sedimentation. So why don't you join me?